which is very often what we want to do with repeated measures. I mean, that's, you know, a great design that we would like to use. But very often we do not meet sphericity. Now, I talked to you about the violation of that assumption, but I didn't tell you, you know, I'm not giving you ways of how to deal with it because that's beyond the scope of this class, you know, or even how to detect it. But I want you to understand that it can be an issue and why it's an issue, right? It's because we have correlations between sets of scores because it's the same people. All right, so what happens sometimes is the correlation between sets of scores is not exactly the same. That can cause issues. That can cause issues. Okay, so, and we may have said this, but just to remind ourselves, a serious problem for a combination of reasons. One, so repeated measures ANOVA is not robust to violations of sphericity. It gives you an issue. And if you violate sphericity, then what can happen is your F ratio is inflated. That means we're increasing our type 1 error rate. So that's the problem with violating sphericity. And this is more serious than violating homogeneity of variance because, one, it's more common, it's more likely. And two, it's a more serious error because it increases our type 1 error rate. Okay? So those are the basics that I want you to know on sphericity. Anybody have questions on it? I just want you to get that basic concept down. Okay, now, we had done those examples, and I made reference to post-hoc comparisons, but I didn't tell you about it because why? The problem is you do your post-hoc comparisons depending on whether you have sphericity or not. That's the basic deal. If you have sphericity, you do one set, and if you don't have sphericity, you do others. Okay? So our post-hoc comparisons, if we have sphericity, and normally you would know this from an SPSS output. Again, I'm not expecting you to know this, but just for your own information, you would get that from the SPSS output. Now, if you have sphericity, you can use any of the post-hoc tests that we've done. What was the error term for our post-hoc tests before? MS within, right? MS within. If you're going to use post-hoc tests with repeated measures, you have to use MS interaction or MS residual. That's your error term. That's your error term. Okay? If you do not have sphericity, you cannot use MS interaction or MS residual. So what can you do? Here's the simplest thing, and the truth is, I know a lot of people who use this often, even if they've met sphericity, and that is just to do matched t-tests, your good old basic matched t-tests between pairs of conditions, but you use a Bonferroni adjusted alpha. Right? Remember, what was a Bonferroni adjusted alpha? We took alpha and divided it into as many tests as we were going to do. Right? That's what the Bonferroni alpha was. If we had 4 tests, we took alpha and divided it by 4. And each test then had an alpha of 0.0125. So this is the same thing. You just do matched t-tests. You take your Bonferroni, you adjust it by the number of tests you're going to do, and you just do that. It's a very simple way of doing it because, you know, matched t-tests are very, very simple. Okay? So the power is not too bad if you do that. And notice this, because I've also been in this situation. It's not even necessary to perform an overall RM ANOVA if you've planned these things out ahead of time and you're adjusting your alpha accordingly. You know, we tend to do it, but it's not even necessary sometimes. Okay? Just in case you're curious, we're not going to do an example on that. I'm not going to hold you responsible for that. I might hold you responsible for saying that what you need to do next, but we aren't going to do the matched t-tests on a repeated measures ANOVA. Okay? Now, what varieties of repeated measures and randomized blocks designs do we have? And some of this should sound familiar because it was similar to the matched T. So you can have a simultaneous repeated measures design. And what's a simultaneous repeated measures design? Let's say I have 3 colors, that I'm presenting people for whatever reason, red, blue, and green. All right? What would be simultaneous presentation? Right? Does it mean exactly the same time? And again, this is from Match T, right? Yeah.
Within the same trial?
It's like within the same session. I don't know that I would say the same trial, but like within the same session. And it's randomized. You know, the red, the blue, and the green, they're randomized within the trial. But you're seeing all of them within the same sitting, you could say. Okay? Now, the problem with that is you still have the possibility of carryover effects. Not simple order effects, but carryover effects. Okay? So that is a simultaneous design. A successive design, again, right? Successive, one after the other. A typical example of that might be is, let's say you're interested in studying drugs for blood pressure. So you give patients a particular drug for blood pressure, and you measure them over a certain amount of time, and then they would test another drug, et cetera, et cetera. It's important to avoid carryover effects. If you're presenting drugs to people, you have to know really well that whatever drug you've just given them is out of their system entirely before you can go on to another drug, right? That would be a carryover effect. So that's an issue. Now, just like with a match T, counterbalancing is necessary, except you're not always going to be able to counterbalance, right? Why can't you always counterbalance? I mentioned this last time. I don't know if anybody was catching it. Let's say you have 4 conditions. So what would a typical order be, right? Person 1 comes in, I give them A, B, C, D. Next person comes in, I give them A, C, B, D. Next one person, right? I could do that. What's the problem with that? Yeah. Yeah, there's too many combinations. It would be 4 factorial combinations of orders. That's not useful. So even though it says counterbalancing, the idea is to get rid of our simple order effects. And I'll talk at the end of this about a different way of doing that. Okay. A repeated measures over time. Again, this is the one that we've done, which is kind of interesting. A significant ANOVA is very often followed by something called analysis of trend components. Again, beyond the scope of this class, but you should know if you come across it that that's what they're doing. Not likely to satisfy sphericity. So here it says use the modified univariate approach. You don't know the modified univariate approach, so don't think you're crazy. I did not teach that to you. So you don't have to worry about that. But it's good to know that you know it's not likely to satisfy sphericity. And it's an extension of a before-after design, so it usually needs a control group of some kind. You can also have a repeated measures design with quantitative levels, right? So far we've used qualitative levels, like time 1, time 2, time 3, right? Or colors or whatever. But you could have it with quantitative levels. But we get back to the same thing. Regression. Regression is often better if your independent variable is quantitative. Right? ANOVA, our independent variable is usually qualitative. It's categories. But when it's quantitative, regression is often better. You still need to worry about counterbalancing. You have to worry about carryover effects. And again, you can follow this with an analysis of trend components. Now, randomized blocks is, again, you analyze it the same way, but you're not using the same people. So again, if I have 5 people for a repeated measures design, and I realize I can't do it as a repeated measures design, but I decide to do it as a randomized blocks design. So let's say I have 3 conditions. How many people do I need for a randomized blocks design in that case? Now, I have 5 people, and I have 3 conditions, but I realize that those 5 people, I can't measure them more than once, but I want to have 5. 15, right? So if it's a randomized blocks design, I actually have to have 15 people. So the benefit of a repeated measures design, one of the benefits is you need fewer people, right? You need fewer people. But in a randomized blocks design, you still need as many people as an independent groups design. But you have more power. You still have more power. That's why people do it. You still have more power. It's not typical, but, it is done. Sometimes people work with naturally occurring blocks. What do we mean by naturally occurring blocks? Families, sports teams, roommates, coworkers. But the problem is, if they're naturally occurring, and we've talked about this all semester, if something is naturally occurring, pre-existing groups, then you can't determine causality, right? Because they're not randomly assigned. All right. Now, if we're doing repeated measures, remember something. Each subject has several scores, right? If you have 3 or 4 conditions, each person is giving you 3 or 4 scores. So these scores vary for 2 reasons. There's 2 things going on here. Each treatment level has a different mean. That means that people vary in their scores, right? Like if I'm one subject and I have 4 scores, well, the scores are going to differ, one, because they're different conditions. They're different conditions, so my scores will vary for that reason. But then the other reason is that there's an interaction between the subject and their own reaction to the treatment. Right? So it's not just the treatment, it's the person's reaction to each individual treatment. So there's 2 sources of variability in there. So if you take a look at this, by the way, this is called a degrees of freedom tree. And it's an interesting way to see how things add up. So if our degrees of freedom total, if this is the formula for degrees of freedom total, then we can divide those total into between subjects and within subjects. And then you'll notice, right, so we have these 3 things. Our degrees of freedom total are made up of between subjects. That would be SS sub, by the way. Okay? The degrees of freedom for treatment, that was SSRM. And then the degrees of freedom for the interaction. That's SS interaction or SS residual. So you can see how they're broken down, and you can actually add those together and see how they work out. And as we're saying here, SS within subjects is made up of SSRM and SS interaction, these 2 sets of variability. Okay, and lastly, this counterbalancing which I said is an issue. Let's talk about how we can tell if we have order effects. Okay? I'm going to show you a simple way to graph things so that it'll help you understand whether you have order effects or not. Okay? You put a dependent variable on that axis, and then the x-axis is what we call the serial position of the presentation of whatever it is you're doing. So like, if I'm presenting 3 colors, red, blue, and green, which is first, which is second, which is third? That's serial position, first, second, and third. Okay? So after I get all my data from everybody, I could set up my numbers so that I could graph it in a different way from graphing the cell means. Okay? So this would be, for example, let's say this is serial position 1, 2, and 3, because I only have 3 conditions. So let's say I have red, okay? And I could graph these in different ways. When red was presented in the first position, then the average came out to be this. When red was presented in the second position, that is, it came second in the order, let's say it was here. And when it was presented third, it came out to be about there. All right? So let's say that's red. I could do the same thing with blue and green. So depending on what this graph looks like can tell you whether you have simple order effects or not. So let's say it falls out like this. And like this. Okay? So what is that an indication of? Well, yeah. Well, there's no interactions, but again, when you're looking at this graph, this is not This is not the analysis of whether there's significance or not with the group means. This is talking about whether you have issues with order of presentation. Yeah?
So because all three went up at the same kind of rate, that means there is kind of some order.
Yeah, it looks like there's some order effects because there's an increase in the performance as everybody gets to 2 and 3. However, there is no interaction. There's no carryover effects or bizarre things going on because there's no crossing of lines. If the lines were parallel, right, red, blue, and green are just like that, then that's an indication you have no order effects. No order effects. And again, if you were actually going to do this, they may not be perfectly parallel, but it might be close enough. Okay? So that is one way that people determine whether there are order effects or not. Okay? So right, horizontal lines, no order effects. Positive slope, you could have a practice effect. Right? People are getting better. If there was a negative slope, it might be fatigue. Okay? Ideal case of simple order effects in this positive slope. Slope would be the same for all conditions, parallel lines. Counterbalancing would solve the problem. Okay? If, however, they're crossed, then you have an interaction as more than simple order effects. You need something different from counterbalancing. And counterbalancing is kind of this overall term, this overall generic term. Like I said, we understand what counterbalancing means, but I'm going to have to show you something that works a little better than that. I don't know if it works better. It's easier to use, implement. Okay, and that's something called a Latin square design. A Latin square design. So let me go back for a minute. And again, it's a way to help you. A Latin square design, again, is a way to help you get rid of simple order effects. Simple order effects. So imagine if I have 4 conditions, right? A, B, C, and D. Okay, I'm just labeling them A, B, C, and D because it's easier to see. But let's say I have 4 conditions. People get presented with A, with B, with C, with D. Okay? In theory, I could create 4 orders, right? I don't want everybody to just get A, B, C, D. I know those are order effects. So I might be tempted to present 4 orders like this. That would be 4 separate orders. That is, person 1 comes in, I give them this first order. Person 2 comes in, I give them the second order. Person 3 comes in, I give them that order. And then person 4 comes in, I give that order. And then I go back to the beginning again for person 5. Now that looks like it would be a good idea, right? It's not. It's not, because the problem is that you're always, one presentation, one stimulus, A, is always being presented before B, right? Like I'm just switching things around each time I get to the next order. So that doesn't take care of it. So this isn't particularly good. Not particularly good. Here's a better thing. Okay? See, a particular level is always preceded by the same other level. Here's a better idea. We start out with this. That's fine. Okay? That's a better set of 4 orders. And again, so you would start with the first person, and they'd get the first order, and the second person would get the second order, and then third, and then fourth. And then when the 5th person comes in, you give them the first order. Right? And you go through it that way. You cycle through it that way. Why is this better? Because each treatment level appears in each ordinal position only once. Right? A shows up in this first position only once. And each level is preceded by each other level once. B is preceded by A only once. So if you have those 2 conditions, that is what we call digram balanced. Here, we can go back to the slide. It's here. Okay? Digram balanced. Digram balance means each treatment level appears in each ordinal position only once, and each level is preceded by each other level once. Okay? That, what we just created there, that was a Latin square design. That was a Latin square design. Right? If you had, by the way, if you had 5 conditions, so the number of orders you would have is 120. Okay? It gets out of control real fast. So Latin square design, the number of orders always equals the number of treatment levels. You know what I mean by treatment levels, right? Conditions. Yeah? So the number of orders, so like we had 4 conditions, A, B, C, and D, so we had 4 levels. Okay? Now, if you have an even number of treatments, even number of conditions, and we'll call that C, then you can create a diagram balanced Latin square design with C orders, like we just did. I had 4 treatments, and I created 1 Latin square design with 4 different orders. If, however, I have an odd number of orders, an odd number of treatments, sorry, like 5, A, B, C, D, and E, then I can't create a Latin square design with one Latin square design. I have to create 2. I have to create 2. So if it's odd, you need 2 Latin square design of C orders each. 2 designs with C orders each. So if I have 5 conditions, A, B, C, D, and E, I have 2 squares of 5 orders each for the 5 conditions. So how many orders is that total that I have? 10 orders. 10 orders. So understand that, right? If I have 5 conditions in my study, then at a minimum, to get rid of counterbalancing, I have 10 orders I have to present to make sure that I get rid of those order effects. Now, 10 orders may also sound like a lot of orders that you have to go through, right? Because it means person 1 comes in, 2, 3, 4, 5, 6, all the way to 10, and then you start back at the beginning again when person 11 comes in. So that might sound a lot, but if the other option is 120 orders for a counterbalance, a complete counterbalance design, then you are definitely going to go for 10. Okay? Do you understand that? Do you understand? Like, I just want to make sure you understand the odd versus the even. Yeah.
No, I'm not sure about the odd versus even. What it means by having why you need the 2 designs.
You need 2 because if you want it to be completely diagram balanced, right? What does diagram balanced mean? Each condition only shows up in each position once, and is preceded by each other one only once. So you need actually 10 orders for that to accomplish that. Is that better? Yeah. Okay? Yeah. Create a Latin square design? No. No. You don't have to create a Latin square design. You really need to know what it is, though. And I mean, for anybody who reads anything else, it's good. It's a simple, easy concept that you're going to come across. All right? So sometimes, though, you can't even do a Latin square design. Sometimes you have so many possible orders that what people do is they choose them randomly. They choose them randomly. And when I mean randomly, I mean really randomly. Not like you look at it and you choose an order, but you use a random number generator in your computer, or you even put numbers in a hat if you had to. But you know, if you have that large number, you probably wouldn't do it that way. But so that's another possibility that people do. Okay? So that's all on Chapter 15. Does anybody have any questions on that? Anything from repeated measures? You're going to be happy with the last chapter. Really? This is easy. And you're going to look at it and you're going to say, wait, that's it? But it's nice to end up with something easier. Yeah, stretch, breathe, yawn. Yeah. Okay. All semester, we've been doing parametric tests. right? I talked about parametric tests, and I said, that this is what we were going to be concentrating on. And again, parametric tests deal with parameters and their distributions. And the parameters we've been dealing with, especially, means and standard deviations, right? But I kept saying, whenever we hit assumptions, right, that you can only do these parametric tests if you meet certain assumptions, and if you don't meet those assumptions, I said, well, very often you'd have to find a non-parametric analog, right, some non-parametric test that is similar. Well, here is the one and only non-parametric test you're going to learn for the entire semester, okay? And it's very easy. All right, so non-parametric tests have very few assumptions, okay? And with parametric tests, we needed interval or ratio level data to do it. For non-parametric tests, we can use categorical data, categorical or ordinal, which is very, very common, right? Like all the polls that are done, all those telephone polls, when people call you up and say, hello, are you in favor of Greenpeace? Are you going to vote for this politician? Which toothpaste do you use? When they do all that marketing research, that's categorical data or frequency data. Frequency data, right? You're counting how frequently people answer yes to a particular category. Now, it says here not as sensitive as parametric tests, it's less powerful. That is not always true. For most of the stuff you would be doing, it is likely to be true, but it's not 100% true. Not 100% true. There are times when a non-parametric test can be pretty powerful. So this last test that I'm going to teach you, and again, we're talking about the test statistic, right? A test statistic was Z or T or F. Those were test statistics. The last test statistic you're going to learn is something called chi-squared. That CHI is pronounced chi. That's the Greek letter chi. Chi-square. Okay? So just like we calculated an F and we needed an F distribution, now we need a chi-square distribution, another table, right? Chi-squares with probabilities associated with it. So it's a probability distribution to deal with questions like, what is the percentage of female professors in physics, or the preferred toothpaste in the United States? So the shape of this chi-square distribution, again, it's not one chi-square distribution, just like there's not one F or one T or one normal distribution, right? A normal distribution depends on means and standard deviations. T and F, those depended on degrees of freedom. So the chi-square distribution also depends on degrees of freedom. So the shape, a chi-square distribution is positively skewed. You may not have been noticing, but the name of it is chi-square. Chi-square, right? You can't get less than 0 with this test, just like F. So it's positively skewed unless the degrees of freedom are large. We're talking about mega large. Because the degrees of freedom for a chi-square are not going to be the number of people or the number of observations. It's not going to be that. Okay, so chi-square can't be less than 0. With infinite degrees of freedom, the chi-square distribution becomes identical to the normal distribution. That's pretty large, right, to get to be normal. And we use it to find the appropriate critical value. We know that. Let's look at an example. Let's see. We have 3 kinds of snacks, and we'd like to know which one, if one is preferred in the United States more often than chance. All right, so here are our snacks. Tortilla chips, potato chips, and cheese doodles. I know, and whenever I do this, like in the morning classes, everybody's like, oh yeah, I'm hungry. So the question is there a preference? Now, the way you do a chi-square distribution is like this. If you'll notice, so we got 90 people, and they answered which one they preferred, right? This little F with an O, that's an O as a subscript. That means the observed frequencies. The observed frequencies, the frequencies, the data that the people are giving you, the observed frequencies. So this means that of that 90, 38 preferred tortilla chips, 28 preferred potato chips, and 24 preferred cheese doodles. Okay? So those are my observed frequencies. That's what people told me. What I'd like to know is based on, is there a preference for one more than chance? So how I have to do that is think, well, if I have 90 people and there's no preference, how many would I expect to fall in each category? How many people would I expect to have a preference for any of those if there is no preference? 30, right? These are what we call the expected frequencies. And this is based on a hypothesis of no difference, right? Essentially here, my null hypothesis, and I'm not going to actually teach you how to write up the null hypothesis, but basically the null hypothesis here is that there's no difference in preference. And if there's no difference in preference, your expected frequencies should be the same. Okay? So the chi-square says, is this distribution of my observed scores, is it different from the distribution of my expected scores? Right? Or is the F observed different from my F expected? Yeah. What? Is 30 what? I took 90 and divided by 3? Okay, yeah. Yeah. No, that's an E. That's a little e. An F sub E. So look at how we test this, folks. This is the chi-square. We take our observed, we minus our expected, we square it, we divide it by expected, and we add it up for each category. That's it. That's it. After 2A Anova, this should look like a relief. Okay, so let's actually do this example. So I look at my first one. So the observed was 38. My expected was 30. I square it and divide by 30. The next one was 28. And then the last one was 24. That's it. That's a chi-square. Okay? All I've done is I've taken my observed and my expected and looked at the differences between them to create this one number. So now, how would I test this for significance? How have we tested everything for significance? Get a critical value. Well, look at the chi-square table. Okay, here's my chi-square table. Now the degrees of freedom for this, I'm going to teach you 2 chi-square tests. The computation is going to be exactly the same, almost. But this first test is called, often it's called a goodness of fit test. A goodness of fit test. Because you're comparing essentially how good your data fit with your theory. It's a goodness of fit test. It's also because we have 3 categories here. It's rather analogous to a one-way Anova, but maybe a little easier to compute, eh? Okay, so in this goodness of fit test, I need the right degrees of freedom to look up my critical value. For this test, my degrees of freedom are going to be k minus 1, where k is the number of categories. K is the number of categories. It's very different from everything we've done so far. So in this example, we have how many categories? 3 rather, right? So we have 2 degrees of freedom. So if we're doing alpha of 0.05, and again, right, it's like an F. All the alpha is up top because it's one-tailed. Why? Because everything that's falling up here is essentially saying that the distributions are different from each other. right? If your value falls up in those tails, it's saying that your expected and your observed are different from each other. If it fell down here, it would be saying that your expected and your observed are close to each other. Okay? So, before we find it, actually, let's take a look. We know that as alpha gets smaller, right? As alpha gets smaller, what happens to my critical value? It gets big. That's typical. But look, what happens as my degrees of freedom get bigger? My critical value also gets bigger. That is very different from anything we've ever done so far, right? It's the opposite of our other tables. As the degrees of freedom increase here, so do the critical values. Okay, because again, it's based on categories, not on the number of subjects. You've got to remember that. So here, what do we have? An alpha of 0.05, 2 degrees of freedom. Our critical value is 5.99. So what is our conclusion here? Yeah, we don't reject. We cannot say that there is a preference for one particular snack food, even though tortilla chips had 38 and cheese doodles had only 24, right? We can't say that there is a preference. Now, part of it comes from, like I said, in general, these non-parametric tests are somewhat less sensitive. So in that case, you need much larger numbers to find those differences. Okay, questions on that? Questions on that? Right, like I said, it's like the simplest test you've done all semester. Yeah?
Is there any way to throw out a category?
Okay. I was going to mention it at the end, but she said, is there any way to throw out a category? What happens sometimes, and I'll mention it again, but sometimes when you're doing things, you find out that you don't need as many categories as you thought. Because, let's say you're looking at age groups in college, right? And then you find, and you're trying to be really generous. Well, let's say, right, like I've taught it at City University as well. So in City University, you have people, of all ages taking classes. Whereas at NYU, generally, everybody is 23 or under, So if I was coming from City University and I was trying to do that here, I might have a category for, 23 to 26 or 26 to 29. And I might realize after looking at the data, like, there's nobody here. So I get rid of it. Or I combine the last two categories or something like that. So that's legitimate. You could be justified in doing that. But your other point was, is there a way to do it to make your critical values smaller? Like, you're not supposed, you know this from the beginning of the semester, you're not supposed to play with your numbers so it gets you the answer you want. But sometimes you are justified in doing some things. Okay. Now, I'm hoping I think you guys have it without this little mess down here. That was a 2 that shouldn't be there. It should be squared. This is just called Yates continuity correction. All this is a correction factor if you're just dealing with 2 categories and your n isn't very large. That's all it is. I'm not going to do an example. You will not be tested on it. Okay? But you should know that you shouldn't just use it. If your n's are small, you shouldn't just use the other formula without this correction factor. That's all. Yeah? No, it's probably smaller than that. She said, what is n too small being? It depends. It depends, but we're not going to worry about that. I'm not going to ask you to make that kind of decision. All right? So, and I mentioned this before, so the chi-square distribution is similar to the F distribution. There's only one tail. Difference is larger than expected by chance, lead to chi-square values in that positive tail. Unusually small values, as they're close together, that's closer to the 0. Right? Only large differences are inconsistent with the null hypothesis. And that's really what it is. That's why I didn't want to call it the null hypothesis before, because really what you're doing is you're seeing whether your distributions are the same as each other. But how you determine what your expected frequencies are kind of are determined by what your hypothesis is. Okay. A significant chi-square tells you there's a mismatch between the expected and the observed frequencies, but you don't know where it is, right? So then you would have to do a Bonferroni, right? You'd have to do the chi-square again for 2 groups at a time and use a Bonferroni. Again, you're not going to do that, but you should know that you have to if you're using 3 or more categories. Now, how do I get these expected frequencies? Well, the set of expected frequencies we just got for this example were based on a particular theory that I have of no preference. In that case, I took my number of observed people, right, that n, and I just divided them equally into the categories, right? That's just a theory of no preference. So that's one way that I can get expected frequencies. There are other ways to get expected frequencies. One is by representation in the population. For example, so here I have blue eyes versus brown eyes versus hazel eyes. But also, what if you were looking at political parties, right? Let's say you're looking that you know in the country there are, I don't know the representation in the country. Let's say 40% Republicans, 40% Democrats, and 20% independents. Okay, I don't think the numbers are that, but let's say that. So then if I select 100 people from Jersey City to see if the distribution of people in Jersey City is the same as the country at large, how many would I expect in each of my categories? Well, how many Republicans would I expect then? 40. How many Democrats? And how many independents? 20. Right? Do you understand that? It's just based on the representation. So in that case, what did I do? What did I actually do to get that? Do you know mathematically? I mean, you just figured it out because you knew. But if I say 40% Republicans, 40% Democrats, 20% independents, and I told you I have 100 people, how did you literally do it? Yeah. 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 If I didn't have 100, how would I do it? What? Yeah, I would multiply by 0.4, right? Or I would take 40% on my calculator, however you're comfortable doing it. We're going to do an example like that, but let's get back to this. Let's talk about the other ways you can get expected frequencies. I think that's the only way I have it? Yeah. Well, yeah, let's actually do the example here. Okay. So here's another example. I just decided because I wanted to have more examples here. So this is the number of flu-related deaths. And these are age categories. Okay, so here's the backstory. In the city from which this sample was selected, 30% of the population is under 30, is in the under 30 bracket, 40% is in the 30 to 60, and 30% is in the over 60. I'm going to read that again. In the city from which this sample was selected, 30% of the population is in the under 30 bracket, 40% is in the 30 to 60 bracket, and 30% is in the over 60 age group. A researcher would like to determine whether any particular age group has a greater risk of flu-related death. A sample, well, how many people did I look at here? 50. And again, looked at, I had to look at records, right? These are people who've died. A sample of 50 cases is categorized according to the victim's age. Okay? Now, so how would I get the expected values here? How do I get my expected values? Yeah.
You multiply 50 by the percentage of the population.
Yeah, exactly, right? So you hear what she said? She said you multiply 50, that's our n, by the percentage of the population, or turn it into a proportion, whatever works for you. So, for example, if 30% of the population is in the under 30 bracket, so what is that? 15, right? It's 0.3 times 50. And there was 40% in the middle bracket. You do the math? Out of 50. 20. Yep. And then the last one was also 15. And again, right, they all have to add up to n. So now we just do our chi-square. Be careful when you're doing this. Notice that your expected values are going to be different. So that denominator is going to be different. Yeah? Yeah. No, sometimes it's not going to be like that. I'm just using simple examples here. No. Yeah, like I said, just be careful, right, that your denominators match up to the right expected frequencies. People make mistakes like that. Okay, and I have to get then what to test this for significance? A critical value, a chi-square critical value with how many degrees of freedom? Yeah, 2. Guess what? It's the same thing as before. That happens a lot when you're doing chi-square examples, because very often when you do examples, there's only 3 categories. It's just kind of common. Not if you were doing actual research, but like the examples that we look at. What's my answer here? Yeah, that's significant. And you can kind of tell, right? Because what you're seeing is that the researchers were trying to show that there are way more deaths in the over 60 age bracket due to flu than in these younger ages. Right? Now again, you would really technically have to follow it up with more chi-squares and a Bonferroni just to show exactly, but I mean it's pretty clear from the data. That's what's going on. Okay? Questions on that? So that was just, what this was an example of was just another way to get expected frequencies. The first way was no preference, and here was based on representation in the population. Those are basically the ones that we're going to deal with. So varieties of one-way chi-square tests. Again, right, they call it one-way because it's like Anova. It's like Anova, but with categorical data. All right? So, and again, it's also referred to as a goodness of fit test. So these varieties. One is when the population proportions are known. Sometimes we know our population parameters, right? The population proportions, right? Like we have statistics for the proportion of crime in a given area or poverty or, you know, a variety of different things. Socioeconomic status, things like that. Number of voters registered to a political party, religious groups. We know that stuff in some places. Sometimes it's done, like if you're comparing 2 populations, like you might want to compare poverty across countries. Okay? Sometimes expected frequencies are hypothesized to be equal. We've done examples like that. sometimes we do this when the shape of the distribution is being tested. The shape of the distribution is being tested, right? Now, like, you might want to know if the distribution of a particular thing is normal. Now, the example I'm going to use is not the best example because I'm going to use ratio level data, but you'll get the basic idea, right? Let's say I wanted to see whether a group of people in Appalachia, and again, we just use one gender, let's say, if their height is normally distributed. So I would take that sample and I would compare the shape of that distribution to the shape, the normal distribution, what I know in the United States. Right? So you could do that. Rejection of the null would imply that the sample shape is not normal. Although, like I said, if you were doing interval or ratio level data, you'd probably use something else, but you get the basic idea. If the sample is truly random, this could mean that the population distribution is not normal. Now, we know for height it is, so that's not applicable to this example. But if your sample says it's not normal, that could imply the population is not normal. If the population is known to be normal, it implies that either your sample is not random or the sample is not from that hypothesized population. So, for example, if those people in Appalachia, if the shape of that distribution was not normal, you would say, wow, the distribution of heights in Appalachia is not normal for whatever reason. Okay? Sometimes we do this because a theoretical model is being tested. You know, people develop certain models that might have expected frequencies or proportions based on the theory behind it. So in that case, what you'd really want is for your observed values to come out like your expected frequencies, because that would bolster your theory. You know, that's more likely to happen in a lab or something like that, if you can manipulate that a little more. People are not so clear-cut. So those come from research hypotheses, not the null. Okay?